Welcome all. Today I am going to take about the topic on sources, resistors, inductors and capacitors which are to be in series and parallel. So first we are going to find the resistors in series. So when resistors are connected in series, the same current passes through all of them. Each resistor has a voltage drop across it given by Ohm's law. V1 is equal to I into R1, V2 equal to I into R2, V3 equal to I into R3. So the total drop in the three resistors when we put together, V is equal to V1 plus V2 plus V3, which is equal to IR1 plus IR2 plus IR3. When as the same current passes through all of them, so V is equal to R1 plus R2 plus R3, the value of I becomes 1, so which is nothing but the equivalent resistance, effective resistance. So R effective resistance equal to R1 plus R2 plus R3. So in a series circuit, the same current passes through all of the resistance. For each resistance, there will be a voltage drop according to Ohm's law. The sum of the voltage drops will be equal to the applied voltage. Next one is resistors when they are connected in parallel. So when resistors are connected across one another such that same voltage is applied to each, then they are said to be resistors are in parallel. So the current in each resistor is different and the current I taken from the supply divides all the three resistors. So the current is I1 is equal to V divided by R1, I2 equal to V divided by R2, I3 is equal to V divided by R3. So the total current is I1 plus I2 plus I3 is equal to V into 1 by R1 plus 1 by R2 plus 1 by R3. So the effective resistance 1 by or effective resistance equal to 1 by R1 plus 1 by R2 plus 1 by R3. If we were to replace the three resistors in parallel by a single equivalent resistor, we must draw the same current I in the circuit which is given by here. So R effective resistance when we have to find, the value will be R1 R2 divided by R1 plus R2. So in a parallel circuit, the voltage across each resistance of the parallel circuit is same. The current in each branch is given by Ohm's law. The total current is equal to the sum of branch currents. Next, inductors in series and parallel. Inductors follow the same mathematical relationships as resistors, but their behavior involves magnetic field interactions and opposition to current changes rather than steady state resistance. So in series inductors, total inductance increases as magnetic fields from each inductor and constructively assuming no mutual coupling between those coils. So when series inductor, the total inductance value becomes sum of all these. So L1 plus L2 plus L3 up to Ln value. In case of parallel inductors, total inductance value decreases as current has multiple paths to establish magnetic fields, reducing overall opposition to current changes. So 1 by L total is equal to 1 by L1, L2 up to Ln. So next one is a capacitor, which is a storage element which can store and deliver energy in electric field. The capacitor is denoted as C. The unit of capacitance is farads. This shows the symbol of capacitor. So series capacitors are total capacitance decreases because the effective plate separation increases. The same charge must be stored across all capacitors, but voltage divides among them. So application of these series capacitors include voltage division, high voltage applications and fine tuning capacitance values. So when capacitors are in parallel, the total effective capacitance becomes sum of all these. So C total equal to C1 plus C2 plus C3 plus etc. up to all these values. So here the total capacitance increases as effective plate area increases. So each capacitor can store charge independently and all experience the same voltage. So application of these include power supply filtering, energy storage systems and motor starting circuits. So for example, take these. So these two capacitors are in parallel. So the total capacitance becomes sum of all these capacitors. So 0.1 plus 0.2 which is equal to 0.3 microfarad. So when resistors are in series with each other, we have to find the inverse of this. So 1 by C total is equal to 1 by 0.1 plus 1 by 0.2, which is nothing but C total is equal to 0.1 cross 0.2 divided by 0.1 plus 0.2. So the total value becomes becomes 0.02 by 0.3. So the total capacitance when they are connected in parallel becomes 0.67 microfarad. So in series circuits, the current flows through a single path, creating unique electrical characteristics, which is having the same current flows through every component in the circuit, and the total voltage divides among components proportional to their individual impedances, and failure of any single component breaks the entire circuit path, causing all components to stop functionally and simultaneously in a series circuits. In case of parallel circuits, which offers independent operation of components, making them ideal for most practical electrical applications, which have a shared voltage, current division and independent operation. So all components experience the same voltage across their terminals equal to the source voltage. Total current divides among branches, which is inversely proportional to each branch's impedance, and then each component operates independently. Failure or removal of one component doesn't affect the operation of others in different branches. So these are the differences between series and parallel circuits of any active or passive elements. Thank you all.